Thank you. So first of all, I would like to thank the organizers for the invitation. I am from a different community. I'm from the high energy cosmic ray community, so it's good to see new faces and speak to fresh minds. So in this slide, you have a very concise summary of what you need to remember about cosmic rays. Cosmic rays are energetic particles that hit the Earth's atmosphere from outer space. Most of them are protons, 90% are protons. And most people believe that they are accelerated as supernova remnant shocks. Now, why is it difficult to study cosmic rays? Because when you do astronomy, you use photons, and photons go straight. Cosmic rays are deflected by magnetic field, and so you cannot do astronomy. If you look the arrival direction of a cosmic ray, it does not point back to the source. So that's why more than 1 century after the discovery, we are still trying to understand where they are from. If we go to low energy cosmic rays, it is even more difficult because this is the spectrum of cosmic rays as a function of energy measured by different instruments. And you see each color corresponds to a different period of time. And you see that the cosmic rays at high energy doesn't change. At low energy, it changes. And it correlates, it has a cycle of 11 years, so it's the sun here. So basically, the solar wind is preventing low energy cosmic rays to enter the solar system. And that's why you have this suppression of the spectrum and these variations. So when you are in the maximum of the solar cycle, the wind pushes more in a more intense way, and so cosmic rays are more suppressed. So the real spectrum of cosmic rays in the interstellar medium is something that you should guess, extrapolating this back and modulating the spectra that you observe. So a breakthrough came when Voyager, the 2 Voyager probes that were launched many years ago, not many years ago because I was already born, so very recently launched. They are now, after more than 40 years, they are now outside of the heliosphere. So basically, both of them. And so basically now they can measure the cosmic ray spectrum, which is most likely not affected by the solar wind. And this is a beautiful picture from a Voyager paper. And basically here you have the counts of cosmic rays, the rate, as a function of time. And it's not, I mean, you go for 40 years almost. And you see that there are these oscillations, which are the solar cycle. So basically but as the probe went further and further away from the sun, then you see that these oscillations become less pronounced, and then here they increase. And so basically you had that this is Voyager 1. So in 2005, it reached the wind termination shock, and in 2012, the heliopause. And you see that after crossing the heliopause, the count rate, this is a zoom of this part of the spectrum, became very stable. And this is considered an indication of the fact that now you are out of the influence of the solar wind. There are some debates about if you are really out, if there is no modulation anymore. But if there is residual modulation, it is very weak. And so now we can complete this spectrum. So here are the spectrum of cosmic rays at the Earth that change at low energy because of the solar cycle. And here are the data from Voyager 1 and 2. And so now we know how the proton spectrum extends down to the lowest point is 3 MeV. We also have a spectra of all nuclei and electrons. Electrons are interesting because you see that the spectrum of electrons, if you compare it with protons, is much steeper. And it is interesting because at high energies, protons dominate by far, by a factor of 100, while at low energies, electrons start to dominate. This is the intensity. So it's a particle per square meter per second per steradian per energy unit. Okay, now if we take the measurement of protons and electrons, and I also added here helium, and we compute the flux of particles. So this is the number of particles flowing across a unit surface per unit time. And in the bottom panel is the same spectrum, but I plotted the spectral energy distribution. So is the amount of energy carried by the particle at a given energy. So you see that if you look up for protons and nuclei, the flux of particles is dominated by energies which are around 100 MeV, 1 GeV. But for electrons, this is not constrained because the spectrum of electrons is steep, and so you don't know how to extrapolate this back. So if you have a cloud, for example, of gas, and you want to know how many particles bombard this cloud, for protons, you can more or less say that, okay, I know the number. For electrons, you don't. If you look the energy, okay, if you integrate this, you get that the number density of particles is this one, of cosmic ray particles in the local interstellar medium. For energy density, is much better because you see that all curves peak here. So the particles that carry most of the energy of cosmic rays have an energy between 100 MeV and a few GeV. Okay, so the energy density is well constrained and the flux is not very well constrained. And the total energy density is 1 electron volt per cubic centimeter, dominated by protons. So now, of course, if you compare the number density with the number density of the ISM, it's ridiculously small. But if you compare the energy density with the energy density of the other components in the ISM, magnetic field, turbulent motion, and so on, they are all in equipartition. So it means that cosmic rays are an important ingredient in the interstellar medium, even if their density is virtually negligible. So before coming here, I tried to think why the two communities, we don't interact too much. I mean, we have interaction, but not too many, because if we typically, cosmic ray physicists want to know where these particles are from. And so the question we ask ourselves is, where do we take the energy to explain this? And so we want basically this GeV part of the spectrum. Or we ask ourselves up to which energy we can accelerate cosmic rays, which are the most extreme accelerators. And so we care about the part of the spectrum which is not here, but is somewhere down here. If you want to know how these particles affect the interstellar medium, you want to know how many particles bombard your cloud, because you want ionization, heating, and so you want MEV stuff. Okay, now these are the spectra that I showed you are spectra measured locally by Voyager EMS, so at the Earth or just outside of the solar wind. What about faraway cosmic rays? So it was proposed in 1952 by Hayakawa that if cosmic rays are everywhere in the galaxy, we should see the galaxy as a bright gamma ray source. And here we are. So Hayakawa was right. If you look the sky in the GeV domain, the most bright source is the galactic disk. And this emission is due to the interaction between cosmic ray protons and protons in the interstellar medium. In this interaction, you do neutral pions, they decay into gamma rays, and you see this. So this tells you that cosmic rays are not a local phenomenon, but they are everywhere in the galaxy. If you want to produce a new pion, you need an energy threshold. So you need that the incoming incident protons must have a kinetic energy larger than 280 MeV. This is important because if we go back to this spectrum, you see that 280 MeV is here. So you see that Voyager and gamma ray data, so gamma ray data constrain the spectrum here, and Voyager here. So these are very complementary instruments. You can, but the gamma ray data tell us something about cosmic rays far away. Voyager is a local measurement. Okay, so now the issue that I will try to discuss is how well we know the spatial distribution of cosmic rays in the galaxy, in the galactic disk. So to do so, we need molecular clouds, because so a cloud is a massive agglomerate of interstellar gas, and as we just saw that cosmic rays are everywhere in the disk, these cosmic rays will bombard the cloud, will produce neutral pions, so molecular clouds are gamma ray sources. If you put a cosmic ray source in the vicinity, you will have more cosmic rays, and so you will have more gamma rays from the cloud. And so that's why clouds are often called cosmic ray barometers, because from the gamma ray flux, we can infer which is the density of cosmic rays at the location of the cloud. Then there is also in the disk a background of soft photons, but this ionizing radiation cannot enter molecular cloud because of the large column density. But cosmic rays can. And cosmic rays, so they enter molecular cloud and they can ionize the gas, and then they can trigger all the chemistry that you are studying. And by observing the molecular lines that result from these chemical networks, you can infer how many low energy cosmic rays you have in the cloud. So basically, the molecular clouds amplify the gamma ray emission due to cosmic ray interaction, because there's a lot of target, and they filter all ionizing agents except for cosmic rays. And so they are perfect tools to study cosmic rays at all energies, from MEV to TeV, and now PV, even with the most recent instruments. So Gamma ray astronomy with clouds is very easy, because if you want to observe a cloud in gamma rays, you build a telescope, you observe, and then basically you know that the gamma ray luminosity from the cloud should be the cross-section for proton-proton interactions times how many cosmic rays you have per cubic centimeter, how many gas particles you have per cubic centimeter, times the volume. So this is just the mass times the density of cosmic rays. So the flux is simply this divided d squared, but from observations, you can measure the gamma ray flux, and from, for example, CO observation, you can measure the mass of the cloud and the distance, and so you can infer how many cosmic rays you have there. And if you do this for a number of clouds, here is a compilation of measurements of this kind as a function of the galactocentric distance. You see that this dashed line is the level of cosmic rays that we have locally, and you see that variations are not big. This is a linear scale, so you have a variations of factor of at most a few throughout the entire disk. So the flux of cosmic rays above 280 MeV, the threshold for pi zero production, is very stable. There are fluctuations of only a factor of a few. Now, you can do the same thing now for the low energy cosmic rays. So you observe H3 plus, CO plus, DCO plus, some of these molecules, and you can infer the ionization rate in the cloud. And this is a compilation of many data as a function of the column density of the cloud. Here is the ionization rate in 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ data are quite dispersed. And you notice that diffuse clouds have a ionization rate which is larger than dense clouds. And then if you try to compare, if you take the spectrum, the local spectrum of cosmic rays measured by Voyager, and you just compute protons, and you just compute which ionization rate you would expect, you have this. So it's not very good. If you do the same for electrons, only the electrons that we observe, so you integrate above 3 MeV, so the lowest energy point in Voyager, you get this. But you remember, electrons are not, the flux of electrons is not well constrained. It is very steep. So if you extrapolate down to low energies, where do you have to stop if you want to match this? And you have to stop at 3 keV. So you really have to do a wild extrapolation from 3 MeV to 3 keV. Now, does this make sense? Can you extrapolate? No, you cannot extrapolate because cosmic rays at low energy lose energy due to ionization losses. And this is a plot showing the loss rate for protons in blue and electrons in red. And I put it in this unit. So basically, this means that a cosmic ray of this energy cools after crossing this column density. Okay. So you see that if you go to beyond GeV, so the energies which are important for gamma ray astronomers, you can easily cross very large column densities without losing energy. So for gamma ray astronomy, these energy losses for protons or electrons are very often not important. But if you go to low energies, you see that even a very small column densities are enough to kill your particles. And this yellow region is the transition between diffuse and dense clouds. I hope I put it right. I'm not an expert of molecular clouds, but this should be something between diffuse and dense. So it means that you remember, for electrons, you have to extrapolate to 3 keV if you want to match the ionization rate. 3 keVs are here. You can cross only 10 to 18 centimeters minus 2. So it means that there is no way that these electrons can enter the cloud and ionize. So if you now do a simple model where you say, my cosmic rays, I take the flux of cosmic rays outside of the cloud exactly as the flux that we measure at Earth, at all energies. And then I assume that cosmic rays go straight. They penetrate along straight line in the cloud. And then I compute the ionization rate. So I take into account energy losses. And this is what I get. Protons is the dashed line, the dotted dash is electrons, and the total is this one. So you see that if you include energy losses, even extrapolating does not suffice. Even an extrapolation does not lead you to match this ionization rate. You can maybe match the ionization rate you observe in dense clouds, but not the one in diffuse clouds. So this is not enough. Then one should ask, is this the good thing to do? We are assuming that cosmic rays go straight. but I told you in the first slide that cosmic rays don't go straight because magnetic fields deflect them. So in fact, this is most likely not the best approximation. So in fact, what one should do is to consider the effect of the magnetic field. And so basically, if you want cosmic rays to enter the cloud, cosmic rays have to stream into the cloud. And if you take a beam of charged particles and you throw them through a magnetized plasma, you trigger plasma instabilities. And there is one of these instabilities called streaming instability, which is responsible for the transport of your cosmic rays. Basically, this means that the straight line approximation is not good, and you should consider some more diffusive transport of cosmic rays in a turbulent magnetic field. Of course, if cosmic rays don't go straight but diffuse, well, the problem is still is more pronounced, because it means that there is more time for energy losses to act on cosmic rays before they can penetrate. And so if you do this calculation, that tomorrow morning there will be a talk by me on this, you get this result. These are still the ionization rates as a function of the column density of the cloud. And the black line is the result of a study that accounts for the effects of the magnetic field. And so you see that now you are below these points at basically all column densities. So and the discrepancy is large. So we have a problem in explaining these ionization rates. So moreover, if you now plot this, you remember was the distribution of high energy cosmic rays that you infer from gamma ray observations as a function of galactocentric distance. If you do the same for low energy cosmic rays, well, this red point here is what you expect. I put it at 8.5 kiloparsec because it's what you expect if you take Voyager spectra, so here locally. Then these blue points are a subset of the points that were in this messy plot with many points. And this selection was made by Neufeld and Wolf-Fire. Basically, these are points where we have more accurate estimate of the ionization rate, and for which we also know the position in the galaxy of these clouds. And then this green point is, from these guys, is the ionization rate in the galactic center. This is linear scale, this is log scale. So it means that here you have variation of orders of magnitude that you need to explain, while here you have only a factor of 2. What is very surprising is that if you look at the galactic center in the gamma rays, you don't see anything special. You see what would be consistent with the background cosmic rays that you observe locally. And if you look at the galactic center in ionization rate, you have 4 orders of magnitudes more than what you would expect. And this is a problem, of course. Now, how can we explain this problem? Probably the first solution that was proposed by Voyager people, so the people that measured this low energy spectrum of protons, is the following. You measure down to 3 MeV, and immediately below that, whoops, you get an extra component that does the ionization. Okay, so this is called the carrot, because it's not the first time that it was proposed. It was proposed also in the 70s, I think, to explain the lithium, the production of lithium. Anyway, you put a carrot, so you put a spectrum that just rises very fast and matches your ionization rates. This is, of course, a possibility, but it is very expensive because the carrot should be below 3 MeV. 3 MeV, we are here. So it means that if you go down here, the energy losses are extremely fast. So it means that if you want to keep this carrot everywhere in the galaxy, you need to pump a lot of energy in cosmic rays. And this is basically, you should pump the same amount of energy here as the one you inject to explain all cosmic rays in the galaxy. So it is a very expensive solution. So probably is not a good one. Then another solution is you put sources inside the cloud. For example, there were people considering, I don't know, protostellar jets, anything. To accelerate MEV particles is not a big deal because it's difficult to go to very high energies. But then, of course, one may ask, there are some starless cores where you observe these high ionization rates. So which are the sources there? Another possibility, which will be also discussed tomorrow in the talk by me, is the following, is that The sun is here. Here is the galactic center. This is a map of the galaxy, and the dots are the position of known supernova remnants in the galaxy. Of course, this is not a complete sample because we miss some of them, especially if you go far away. But this tells you that the injection of cosmic rays in the galaxy is not a continuous injection everywhere in the disk, but you have point sources injecting particles, and these are also supernovae, so they explode. So you have to imagine some stochastic injection in both time and space. So if you do so, you have to remember, maybe I can go back, you have to, this plot is good. You have to remember that in the energy range that you need for ionization, energy losses are quite important. Where in the energy range important for gamma ray observations, the losses are not important. So it means that if you have this stochasticity, for gamma ray astronomers is not a big deal because these particles don't lose energy. So they will mix, they will fill the disk, and they will do a uniform fog of cosmic rays. But at low energies, this is not the case. So you may expect fluctuations because if you are not close in time and space to a source, these particles cannot reach you. So the idea that we try to test here is what happens if you consider the stochasticity of the sources. And what you get here is that these are the data for protons and electrons, and the solid black line is the median of your realization. I mean, you run many different realizations of where supernova are and when they explode, and you see that the median fits well both protons and electrons. The dashed, the colored regions are the fluctuations around this median. And you see that at high energy, as expected, there are no fluctuations. But if you go to the MEV domain, fluctuations start to be important. And so it could be that some of the large ionization rate may be explained by the fact that the cloud that you are observing sees a spectrum which is this one and not this one, and so you increase the ionization rate. But Min will give more details tomorrow morning. Okay. So basically, the message is that we do not understand yet the origin of the high ionization rates observed in cloud. And there are some questions that we need still to answer. First of all, why we see these large ionization rates? And then the other question, which is very important, is are low energy cosmic rays measured in the local ISM representative of the galaxy, or they just represent some local stuff? And then there are other questions. For example, atomic and molecular clouds do not show any different trend in the ionization rate, even if they have different column densities. So why is that? We don't understand. And then the galactic center, of course, it's 4 orders of magnitude more than what you expect. So I have no idea why. And then we have to understand where are the sites of acceleration of low energy cosmic rays, because nobody guarantees that high energy cosmic rays and low energy cosmic rays have the same sources. It is very easy to accelerate MEV particles. It is very difficult to accelerate PV particles. So you may have many more possible sources of MEV cosmic rays than high energy cosmic rays. And then there is another thing that we should remember is that we are inside the local bubble. So we are not in the typical interstellar medium. We are inside a cavity inflated by the explosion of many supernovae. And this may affect what we see, especially at low energies, because at high energy, I mean, these particles move so fast that it's difficult to think that we may be affected. But we should remember that we are in the local bubble. So it could be also that we see a low flux of cosmic rays because we are in a special place in the galaxy. Now, I just briefly conclude on the future, but I have only a couple of slides more. So the future in this field of research is JWST, because I think this stuff you know better than me. It was, for example, proposed by Marco Padovani et al. That you could see with WJST the raw vibrational line emission. So basically, with cosmic ray, you ionize H2, and the secondary electron excites the H2, and you see this line. And this is a very clean network. I mean, there is not many reactions involved, so it's quite direct measurement of the cosmic ray ionization rate. X-rays. Athena is important because X-rays. In the X-rays, you can see the iron K alpha line at 6.4 keV, which is produced when you ionize the cold gas. You can do it either with photoionization, so you take a cold gas and you bomb it with X-rays, or with cosmic rays. And there are some preliminary evidences with Suzaku of this line from clouds located very close to supernova remnant shocks. So in places where you expect a large density of cosmic rays. And so in the future, detecting this line from many clouds would be of help in constraining the spectrum of low energy cosmic rays. MEV astronomy, it would be great to have eAstrogam, which is a satellite in the MEV domain, because low energy cosmic rays can also excite nuclei, atomic nuclei. And so you expect to see nuclear excitation lines in the MEV domain. And if you build this guy here, you should be able to see these lines if you integrate the entire inner galaxy. And so this will tell us something about the global content of the galaxy in low energy cosmic rays. And then, of course, SKA, because cosmic ray, low energy cosmic ray electrons do synchrotron radiation in radio. And these green, blue, and red lines show you which energies are important for SKA if you change the magnetic field. And I think that's it. Thank you.